we have a triangle with angles alpha, beta, and gamma, and this here is the incenter of the triangle, so the intersection point of the angle bisectors in the triangle. And this is also the center of the incircle of the triangle, so if we drop a perpendicular to this side, this will be the point of tangency of the incircle and this side of the triangle, and so this length is r, the in radius of the triangle, or the radius of the incircle. And we can intersect this angle bisector with this side here, and we can note that this side is 2r times sine of alpha, and this side is 2r times sine of beta because of the law of sines, where r, big R, is the radius of the circumcircle of the triangle, so the circumradius. But first, I want to walk you through some calculations. We know that alpha plus beta plus gamma is 180 degrees. Therefore, when we divide this by 2, we get that alpha over 2 plus beta over 2 plus gamma over 2 equals half of 180 degrees, so 90 degrees. And therefore, alpha over 2 plus gamma over 2 equals 90 minus beta over 2. And now if we take the sine of both sides, we get that the sine of alpha over 2 plus gamma over 2 equals sine of 90 minus beta over 2. And now notice that sine of 180 minus alpha over 2 minus gamma over 2 equals sine of alpha over 2 plus gamma over 2, because the sum of this and this is 180 degrees. And then sine of this equals sine of 90 minus beta over 2, which is cosine of beta over 2, because the sum of this and this is 90 degrees. Notice that beta plus gamma over 2 equals 90 minus alpha minus beta over 2, and this follows straight from this equality. If you replace 90 degrees with alpha over 2 plus beta over 2 plus gamma over 2, you're going to see that everything cancels out. And now take the sine of both sides, and you get that sine of beta plus gamma over 2 equals sine of 90 minus alpha minus beta over 2, which equals cosine of alpha minus beta over 2, because this plus this is 90 degrees. The sum of the angles in this triangle gives that this angle is 180 minus beta minus gamma over 2. And so the complementary angle is beta plus gamma over 2. Similarly, the sum of the angles in this triangle is 180, and so this angle must be 180 minus alpha over 2 minus gamma over 2. I'm going to denote this segment by x, this segment by z, and this segment by y. And then let's find expressions for x, y, z, r, and x plus z, where x plus z is the length of the whole angle bisector. We apply the law of sines for this triangle, and we get that x equals 2r sine beta times the sine of alpha over 2 divided by the sine of this angle, so which is written here. But we know that sine of 180 minus alpha over 2 minus gamma over 2 equals cosine of beta over 2. And therefore, we can rewrite this expression like that, and this is our final answer for x. Similarly, we can find the length of y. Applying the law of sines for this triangle, we get that y equals 2r sine beta times sine of gamma over 2 divided by the sine of this angle. But we know that sine of 180 minus alpha over 2 minus gamma over 2 equals cosine of beta over 2. And so we can rewrite this expression like that. And this is the final answer for y. To find z, we can apply the law of sines for this triangle, and then we get z equals y times sine of alpha over 2 divided by sine of beta plus gamma over 2. But we know that sine of beta plus gamma over 2 equals cosine of alpha minus beta divided by 2. And so the final expression for z would be, we take y and we substitute it, and then we multiply sine of alpha over 2, and then we divide by cosine of alpha minus beta over 2. To find r, we can use this right angle triangle with hypotenuse y, and this angle is alpha over 2, and so r equals y times sine of alpha over 2, which is written here. And then we just replace the y from here, and then we get this expression for r. Finally, to find x plus z, we will use a sine theorem for this triangle, and then we get x plus z equals 2r sine beta times sine of alpha divided by the sine of beta plus gamma over 2, which is written here. And now, sine of beta plus gamma over 2, we know that it equals cosine of alpha minus beta over 2, so we can rewrite this expression like that, and this would be our final answer. Take a look at this isosceles triangle. It has an angle beta over 2 and beta over 2 here, and this angle must be 90 minus beta over 2, because this is an angle bisector and an altitude here, and it's also a median. By the sine law applied for this triangle, we have that this side is 2 times r times the sine of this angle, where r here stands for the circumradius of this triangle, so the radius of this circumcircle. But we know that sine of 90 minus beta over 2 equals cosine of beta over 2. So this side is essentially 2r cosine of beta over 2. And now from this right angle triangle, we can find that this side is this side times the sine of beta over 2. So 2r cosine beta over 2 times sine of beta over 2. We know that this side equals this side, so essentially the whole side is 4 times r cosine beta over 2 sine beta over 2. But we know that the whole side, from the law of sines for this triangle, equals 2 times r sine of this whole angle, which is beta, so 2r sine of beta. And therefore, 4r cosine beta over 2 sine beta over 2 equals 2r sine beta equals the length of this side of the triangle. We can cancel out 2r here, and then we get this formula for sine beta. Sine beta equals 2 times sine beta over 2 times cosine beta over 2. And then we can replace this sine beta, this sine beta, this sine beta, and this sine beta with this formula in order to cancel out the cosine of beta over 2 in the denominator. And so when we do that, we get these 4 identities here. And maybe the most important one is this one, which says that the in-radius of the triangle equals 4 times the circumradius of the triangle times the product of the sines of the half angles of the triangle. Here you can see the final results and the picture at the same time. Here's the optional problem. We have a triangle, and this is its circumcircle, and this red dashed line here is the tangent line to the circumcircle at this point. This and this are angle bisectors in the triangle, and they intersect the circumcircle and the sides of the triangle at these 4 points. And then we take this line and this line. We need to prove that these 3 dashed red lines intersect at one point. And here's the solution. First, let's make the drawing a little bit larger. Now let's call the angles of the triangle alpha, beta, and gamma. Then because these are angle bisectors, this is alpha over 2, this is alpha over 2, and this is beta over 2, and this is beta over 2. And also we have that this angle is 180 minus alpha over 2 minus beta over 2 because of the sum of the angles in this triangle. And therefore this angle is alpha over 2 plus beta over 2. But we know that alpha over 2 plus beta over 2 plus gamma over 2 is 90 degrees, and therefore this angle can also be written as 90 minus gamma over 2. We know that this quadrilateral here is cyclic, and therefore this angle equals this angle, and this angle equals this angle. So here we have alpha over 2, and here we have alpha over 2. Similarly, this quadrilateral is cyclic, and therefore this angle beta over 2 equals this angle beta over 2, and this angle beta over 2 equals this angle beta over 2. Also, this angle is gamma, so it corresponds to this arc, and hence it equals this angle, which also corresponds to this arc, and this angle, which also corresponds to this arc. Finally, this is a tangent line to the circumcircle, and therefore this angle corresponds to this segment, and therefore it equals this angle by the alternate segment theorem. And so we have alpha over 2 here. Now let's intersect this line with this line and with this line. So the intersection of this line and this line is here, and the intersection of this line and this line is here. And let's call this distance x and this distance y. We're going to prove that x equals y, from which it would follow that this point and this point coincide, meaning that the 3 red lines intersect at one point. We're also going to call this segment here z. Let's label this distance m, this distance n, this distance d, and this distance e. We're going to apply Menelaus theorem for this triangle and this point, and this point lying on each of its sides. Then z plus x divided by x times e divided by d times n divided by m equals 1, which is written here. Now let's apply the law of sines for this triangle and this triangle. We get that e divided by d equals sine of alpha over 2 divided by sine of beta over 2 times sine of 90 minus gamma over 2, which equals cosine of gamma over 2, divided by sine of gamma, which is written here. And now we know that sine of gamma equals 2 times sine of gamma over 2 cosine of gamma over 2, and so we can cancel out the cosine of gamma over 2, and we get sine of alpha over 2 coming from here, and then sine of beta over 2 coming from here, and then the remaining part of sine of gamma is 2 times sine of gamma over 2. Similarly, we can apply the law of sines for this triangle, and we get that n divided by m equals sine of alpha over 2 divided by sine of beta over 2 times sine of gamma divided by the sine of this angle, which is cosine of gamma over 2, but we know that sine of gamma divided by cosine of gamma over 2 equals 2 times sine of gamma over 2. And so the final result for n divided by m would be sine of alpha over 2 divided by sine of beta over 2 times 2 sine of gamma over 2. And so from here we can find e divided by d times n divided by m by just multiplying this expression times this expression. And now the 2's cancel out, the sine of gamma over 2 cancels out, and what's left is sine of alpha over 2 times sine of alpha over 2, which is here, and sine of beta over 2 times sine of beta over 2 in the denominator, which is here. And so we get this expression, which we can substitute here and get an expression for z plus x divided by x. This here is the final expression for z plus x divided by x. Now we're going to find z plus y divided by y. And we're going to do it by applying the law of sines for this triangle and this small triangle here. Then we get that z plus y divided by y equals this whole angle divided by this small angle here, alpha over 2. So we get sine of alpha plus gamma plus beta over 2, which is this whole angle, divided by sine of alpha over 2, which is here, and then times this angle, beta over 2, divided by this angle, alpha over 2. But we know that this sine equals sine of beta over 2 because the sum of beta over 2 and alpha plus gamma plus beta over 2 is 180 degrees, since alpha plus beta plus gamma is of course 180 degrees. And therefore this expression turns into sine squared of beta over 2 divided by sine squared of alpha over 2, which is exactly the same as this expression. And therefore z plus y divided by y equals z plus x divided by x. And from here we can subtract 1 from both sides of the equality and get z divided by y equals z divided by x, and canceling out the z, we get that y equals x, which means that this point and this point coincide, meaning that the three red lines intersect at one point.